So I hope my screen is visible now.
Yes, sir.
Okay. Uh, Please let me know if the meeting is discontinued. Otherwise, I was talking for like 10 minutes yesterday, and then when you called me, I realized that the meeting is disconnected. Right?
Okay.
Okay.
Yes, sir. Sir, actually, what happened? I was like saying in the speaker, but due to internet connection, I think that wasn't audible. So that's why I called
Okay.
after that.
Okay.
No
Okay.
problem, sir.
Huh?
Like we have done till we are starting to with the third command, the last command for that thing.
Okay. Okay. So today in our agenda, then we have free energy estimation and the remaining part of the cluster analysis that we have left last time, right?
Yes, sir.
Okay. So I hope that you have heard till this thing. Okay, what are these? Or shall I explain you?
Sir, can you explain it again? Like you have given the briefer idea that there were like two conformations or the
Yes.
dimensionality which has been explained, and one is major and one is minor.
Yes, yes. So
Yes.
the thing is that ideally you should adjust your RMSD value in such a way that you should get two clusters. Sorry, you should get a single cluster. Sorry. Huh? So
Yes.
where is that you need to do that is in I will tell you in this command. Okay, over here, right? So here we are giving the RMSD cutoff of 0.11 nanometer, right? So the thing is that if you kind of end up getting multiple clusters like this, okay, then your approach should be to obtain a single cluster that will encompass the entire trajectory, okay, and you can do that by increasing the cutoff value of RMSD, right? But make sure that whatever value you increase, it should not go beyond 0.2 nanometer. Okay,
Yes, sir.
so try to kind of play around with this RMSD cutoff value and try to get the single cluster, right? And when you get a single cluster or even majority of frames are present in second cluster, so we can go with this cluster now, right? There is no issue, but try to make an attempt that you obtain a single cluster, right, by changing this RMSD cutoff value. In the command we gave 0.11. Whatever you change, just make sure that it should not exceed 0.2 nanometer. Okay, so
Yes.
make that rearrangement then. Okay, so next thing that is important is that this this number correspond to the time step in your simulation, specifically in picoseconds in our case, where we have figured out ki at this particular moment in our simulation we have our representative frame, right? So the next job will be to extract this particular frame at this particular time point in our simulation and then analyze it, right? And for doing that we have another command, this one, for extracting, right? So for extracting, dash f will give the name of input file, the name of trajectory file, xtc file that we have generated. Then dash s is the option where you provide the name of the structure file, which is in form of ionized.bro, right? And dash o will be the name of the file in which your cluster analysis frame will be saved, right? And this dash dump command will tell Gromax that you need to save the frame with this particular time step as such. Okay,
Yes, sir.
this is what this command means. So now what I will do, I will try to dump this frame. Okay, I have already done this thing, but I will do it once more, right?
Sir, this can also be helpful in like superimposition thing, na? Cause in many research articles I have
Yes, of
read.
course, yes, of course, we can do that. I will tell you how is that this can be done as well. कोई दिक्कत नहीं है, right?
Yes.
Okay, we will start our Gromex program, right? Because that is what we are using. Then go to this test, and since we are in C drive, we don't have to change the drive. All we have to do is to give the C the directory command and just simply paste the paste the path where we have our working directory, right, which is currently in test folder, and make sure that whatever command that you are supposed to give, we have got. I'm copying this thing, this dumping command, okay, and I am simply pasting it over here, right? So do we have a renumber.xtc over here? Yes, we have renumber.xtc, we have ionize.grow, and everything else is then regenerated. Okay, so all we have to do is to hit enter. Okay, now it is asking as to what is that you want to save in that protein file from our trajectory, right? So we would save the state of entire system containing water molecule, protein, as well as ligand, and if there are any ions, the entire system at that particular time step. Okay, so we would select the 0 option and hit enter. And now it will go on looking for that particular frame, and when it finds out, it will save it as a PDB file. That is what it does, right? So it
Yes, sir.
has saved this file, right? And this file, if you try to open it, it will be a very big file, because it will contain all the water molecules and everything. Okay, it might even take some time, right? So this is the entire system that we have saved in a trajectory file, in a PDB file from the trajectory well, say for example, right? But now what we need to do is to get rid of all these water molecule, because we won't need them anyways. So let us close this thing, and next thing that we need to do is that we need to open it in our favorite text editor, right? Locate from where we start out the water description. Okay, in our simulation we have this TIP3 water model that we have used, right? So all the atom that contains TIP3 description in their name, we need to delete them. Why? Because we simply don't need water molecule, it will simply create problem. And in a, an ideal PDB format, this termination line should be present where the description of your protein molecule ends up, right? It should be ideally present over here, and this uh, end line will indicate that the information in a PDB file is over. So in this way, your SPDBV or any structure visualization program, even your Discovery Studio will recognize this. Okay, this is the line above this contains protein, and the line below this contains the ligand, right? And beyond this line, we have got nothing. That is what this means. Okay, I hope you understand this. Then, okay, so we are done with this thing. Now let us think as to how is that we will evaluate our results, or how is that we would analyze whatever we have obtained in our cluster analysis. So clearly, this particular file now contain the results, or you can say the representative pose from our MD simulation. Okay, so we have this thing, we can open it, simply open it in SPDBV, that will work. Okay, just hit OK, right? And let me show it in ribbon representation, and let us show our ligand in lines representation. Okay, so this is our result, or you can say a representative frame from MD simulation, right? And what we will do, we will compare whatever we have obtained as a representative frame from MD simulation with the initial state of our system from where we have started docking, where we have started MD simulation, sorry, right? So the thing is that we usually start our MD simulation right from the docking results, right? So over here I have the result from my docking, right? I will load those results, right? And over here you can see that here I have my docking result, right? And here I have my ligand, right? So
Yes.
this is what you can see that this is the state of your system when you begin the simulation, and this is the state of your system which was found to be most predominantly exist in the MD simulation as such, or you can say that this is the representative pose. This is the state of your protein that was present throughout the trajectory, you can say, more or less, right?
Oh,
So now
yes.
if you just push this control tab after loading uh, these two protein, or you can say the same protein at different time state, then you can see that this is how the conformational changes have happened. Okay, so now let us focus only on the ligand molecule, right? So if we focus our view on ligand molecule, this is the pose from you can say cluster analysis, that is the pose from MD simulation trajectory, and this is the pose from the initial confirmation. Now you can see a lot of things have happened over here. Initially the you can say this is the hydroxyl group that is present. It was oriented in this way in your protein, right? But now during simulation it has changed the conformation, and maybe it has obtained some another pose, and your hydroxyl group now is oriented in say some different conformation. दिख रहा है आपको?
Yes, sir.
Okay, so now what we will do, we would try to compare what is that is happening at the binding site when such two conformations are in comparison, right? तो उसके लिए what we will do is that we will try to create a 2D representation. We will try to create a 2D representation of what is happening around your ligand molecule when it was present in the docking pose, and whatever we have observed in our cluster analysis result. Okay, so how is that we do it? It is quite really simple, not a big deal. So do you understood how is that we work with Gromax in Windows operating system? ये समझ में आ गया
Yes,
क्या
sir.
आपको? It is quite really very easy, right? If
Yes.
I would expect you that you try out different you can say try out different tutorials for the Gromax. I have just shown you as to how we can use it for cluster analysis, right?
यस सर।
So
सर मैंने भी
this software
वही वाला
can
डाउन यस सर।
हाँ बोलो।
सर मैंने भी सर वही वाला डाउनलोड किया था सर जो आपने ग्रोविन का बताया था।
हाँ हाँ।
बट सर जैसे ग्रोमैक्स में नए-नए वर्जन्स आते रहते हैं तो और वो रिलीज़ होते हैं लिनक्स में ही। तो
हम्म।
सर कोई फ़र्क पड़ता है क्या नए वर्जन्स वगैरह से कुछ
ज्यादा फर्क
ऐसा?
नहीं रहता है, ज्यादा फर्क
ओके,
नहीं रहता है,
ओके
ठीक है?
सर।
So you can easily use this. Why? Because it is really very easy to install and use, right? You can use it in your teaching assignments, right?
यस सर,
I mean, everyone has Windows, and this thing works really very well,
एग्ज़ैक्टली सर।
right?
यस
So
सर।
try using it in your teaching and research if possible. Okay, And also I want you to write a review after using this Gromax on sourceforge.net. Hoga?
Yes, sir. Pakka.
Okay, try using it for cluster and mention in that review on SourceForge that I have used it for cluster analysis and I have found it, and give 5 star.
Sure,
Right.
sir. 100%. Okay.
Okay, so shall I close this thing now?
Yes, sir.
Okay, now in our agenda what we have is this thing. Okay, we have also done this frame extraction, right? So frame extract ho gayi, and now it is time for us to analyze this thing. Okay, so now what I will do is I will open first the docking pose, right? I will open it with the Discovery Studio. This will be the start of your simulation, right? The very initial pose from where you have begin the simulation. बरोबर है?
Yes, sir.
So in this Discovery Studio, you can create a 2D representation of what is happening at the binding site where your ligand is, right? And for doing that, go to this mouse model and select rotation. Okay, and you can do that in this receptor ligand interaction tab. You have this show 2D diagram over here. Okay, when you click this show 2D diagram, you will see as to what was the interaction when you begin the simulation, right? So now what we will do, we will save this thing. Okay, what is that you can observe over here, that the hydroxyl group that was present in your inhibitor, it formed hydrogen bond with the tyrosine at position 385, and it showed some pi sigma interaction with these two amino acid residue. The pi electron density uh, from your phenyl group, and the sigma group from the valine and leucine. So pi sigma interaction is shown over here, and there are other things like your pi alkyl interaction भी हो रहा है यहाँ पर between this particular phenyl ring and leucine 520, and others are the residues that are present in van der Waal contact. So it is quite self-explanatory, right? I don't have to explain this to you. I think you are in position to re-evaluate these simple things. Okay, so now what we will do is that we will save this 2D interaction at the active site when we begin the simulation, right? And in desktop we have test, right? And I will save it by the same name. I have already done it. It will ask me if you want to replace it. Yes, I want to replace it. Let us make it bigger. We'll say for example like 2000 pixels on width, and appropriately it will change the height. So just hit OK, and your state will be saved, right? So now let us do the same with the results that we have obtained from cluster analysis, right? For doing that, go to file and then open, right? And this is the molecule that we have saved right away. Open it, right? And we will do the same thing. Go to receptor ligand interaction tab, and we will show the 2D representation. Okay, and now you will realize that whatever tyrosine molecule that it was initially showing hydrogen bond, it is no longer in hydrogen bonding distance. In fact, these two hydrogen bond appeared that were missing in your molecular docking study, right?
Yes, sir.
Okay, so this is the ultimate objective of doing cluster analysis, to figure out as to are there any interaction that we are missing when we perform docking, right? When we perform docking, we get a static pose, right? And when we perform MD simulation, some interaction will be disrupted, and your ligand molecule can form some very you can say some very stable interaction when the functional group in your ligand molecule will orient itself in the binding site of your protein, right? So the thing is that we will compare these things anyways, so that you will get a complete idea as to what happened during MD simulation, right? And let us again save it as an image file. Okay, let us keep the same name so that uh, we can use it for comparison, right? Again we will use the same dimension for saving and hit OK. Okay, now the 2D representation of our active site before we started MD simulation and after we did cluster analysis is ready, right? So what I will do is that I will compare these two results, and I have already done this thing and I will show you over here. So on the left hand side you can see that this is the result from docking, and from right hand side you can see that these are the results from cluster analysis of
Dynamic.
MD simulation, right? So what is that you can observe now? This is how you should discuss your result in your paper. Okay, so you can start out like saying ki in the molecular docking result, uh, tyrosine 385 was found to be in hydrogen bonding distance from the hydroxyl group of the ligand, but during the subsequent MD simulation this tyrosine 385 hydrogen bond was found to be transient. Instead, the ligand oriented itself in the active site of the protein and form a very stable hydrogen bond with methionine 522 and serine 530, right? इस
Yes.
तरीके से अपने को लिखना है आपके ट्रेजेक्टरी में. दिस इज हाउ यू राइट द रिजल्ट्स, राइट? Additionally, we have figured out that phenylalanine 381 glycine 526 might form the pi-pi T-shape interaction that were missed during docking, right?
Yes.
And alanine 572 forms a very stable pi sigma interaction as compared to valine 523 and leucine 522. These pi sigma bonds were found to be transient or unstable, right? इस तरीके से क्या करने का, इसको कंपेयर करने का. Okay, so now how is that you can represent these dynamics of hydrogen bond, राइट? हाउ इज दैट यू कैन शो कि भाई ये जो टायरोसिन है इस ये ट्रेजेक्टरी में एग्जैक्टली कब ये दूर चले गया, या कब ये हाइड्रोजन बॉन्ड ब्रेक हो गया, या कब ये हाइड्रोजन बॉन्ड फॉर्म हुआ, या कब ये हाइड्रोजन बॉन्ड फॉर्म हुआ. ये सारी चीजें अपन रिप्रेजेंट कर सकते हैं क्या? यहाँ पर तो सिर्फ अपन बता सकते हैं कि during simulation somewhere in some time step this hydrogen bond was disrupted and this hydrogen bond was formed and these two hydrogen bonds were formed. बरोबर है?
Yes, sir.
हाँ, तो ये अपन एक्सप्रेस कैसा कर सकते कि भाई इट वुड बी रियली वेरी इंटरेस्टिंग टू टेल कि ओके दैट दिस हाइड्रोजन बॉन्ड वाज फाउंड टू बी इंटैक्ट टिल first 10 picosecond, well say for example, and then these hydrogen bond were found to be formed, this particular hydrogen bond formed at 50th nanosecond or say for example 20th nanosecond, and it remain intact throughout the simulation, right? तो ये टाइप का एनालिसिस आप कर सकते हैं इफ you do distance based analysis or try to plot the distance between these amino acid residue and this hydroxyl group. Okay, so if you plot what is the distance of methionine का जो हाइड्रोक्सिल ग्रुप होगा और ये जो हाइड्रोक्सिल ग्रुप है इसके बीच में जो कुछ भी हाइड्रोजन बॉन्ड, इफ यू कैन ट्रेस आउट कि भाई व्हाट वाज दिस हाइड्रोजन बॉन्डिंग डिस्टेंस थ्रू आउट द सिमुलेशन, then you can say ki, okay, at this point this hydrogen bond form and at that particular point it was disrupted, right? Do you get what I am trying to say? समझ में आ रहा है क्या आपको?
Yes.
Okay,
Yes, sir.
so how is that I have done, I will kind of tell you. तो मैं क्या करता हूँ, आपको मेरा पेपर बताता हूँ जिसमें ये चीज़ मैंने पब्लिश की है, राइट? आई विल शो दैट पेपर। ये क्या क्या 7HFN का किया था ना अपन ने in this case. So we have published this particular simulation in this journal of biomolecular structure and dynamics. Are you aware of this journal?
Yes, sir.
Okay, so I have kind of published it back in, ये कब की बात है रे भाई, 2019 I suppose, right? तो उसका इम्पैक्ट फैक्टर क्या है मालूम है क्या आपको? लेट अस सी। ओ इट इज क्या है अभी?
6.25.
ओके,
6.25.
it is a good journal, नहीं क्या? Okay, anyhow,
Yes.
so in this journal, in this paper, I have tried to do this kind of analysis, like comparing the hydrogen bonding dynamics that happened during MD simulation. Okay, and I have kind of, let us focus on a lot of things happened in this paper. Okay, like homo lumo and DFT and everything. This is RMSD, RMSF, as we have already discussed. Okay, I remember doing that thing. 7HFN. Yes, here it is. Okay, 7HFN. Right. So what I have done is that I have tried to plot this tyrosine 385 hydrogen bond. Do you see? Tyrosine 385.
Yes.
This tyrosine 385. Okay, I think now it is clear. जो blue color का है, right? Now, as we can see in docking, it form a hydrogen bond over here, right? So that means in our trajectory, when we started the simulation, this tyrosine 385 hydroxyl group and ligand का ये जो hydroxyl group था, well, they were in hydrogen bonding distance of 3.36 angstrom, right? Which is shown over here. Okay, and now somehow this hydrogen bond remain intact till 10 nanosecond, as you can see over here. But later on, some conformational changes happen and the ligand reoriented itself and it lost the hydrogen bond, as the hydrogen bonding distance now is around, now the distance between these two atoms is around what? 8 angstrom, right? And you can see that this distance between the two atom remain around this 8 angstrom throughout the trajectory. दिख रहा है?
Yes. Yes.
बरोबर है ना? So this is
Yes.
how you can say, right? And at the same time, you can consider what happened with the hydrogen bond for serine 530, जो रेड में बताया है, राइट? तो रेड में सिमुलेशन के शुरुआत में इट वाज अराउंड 8 एंगस्ट्रॉम, राइट? दिख रहा है ना यहाँ पर? एंड द टाइम व्हेन दिस स्विचिंग हैपेंड, राइट? यहाँ पर क्या दिख रहा है आपको? स्विचिंग हो गया, राइट? दिस टायरोसिन 385 के साथ में जो हाइड्रोजन बॉन्ड था, दैट वाज स्विच्ड विद serine 530 at this particular moment in the trajectory, right? ये दूर हो गया, at the same time ये पास में आ गया, बरोबर है? The same moment tyrosine 385 got away from your ligand molecule, at the same moment during the same time your serine 530 got the same hydrogen bond, बरोबर है? And then somehow it remain intact around 3 के आसपास ये भी हाइड्रोजन बॉन्ड स्टेबल रहा थ्रू आउट द ट्रैजेक्टरी. दिस इज व्हाट दिस ग्राफ मीन्स. ओके, समझ में आ रहा है क्या आपको?
Yes,
Yes,
sir.
sir.
Okay, so what happened with methionine 522? you can see that methionine 522 के साथ में क्या हुआ, right? So initially you can see the hydrogen bonding distance was around 9 point या 10 के आसपास, right? मतलब they were not in hydrogen bonding distance. ये कब तक हुआ? अराउंड 10, क्या कह सकते हैं आप, ड्यूरिंग 10 नैनोसेकंड. 10 नैनोसेकंड में यहाँ पर भी काफ़ी रीअरेंजमेंट हुआ, राइट? And after this rearrangement, around 15 nanosecond, a very stable hydrogen bond was formed between methionine 502 and ligand का जो ऑक्सीजन ग्रुप है उसके साथ, right? And that remain intact throughout the simulation, as you can see. बरोबर है? So
यस, तो सर इसके लिए तो अपन को फ्रेम बाय फ्रेम स्टडी करना पड़ेगा कि कब हाइड्रोजन बॉन्डिंग को
so
चेंज
now
हुआ.
I will tell you how is that you save this data and how is that you prepare such a kind of graph, so that you can express such a kind of analysis,
यस.
right? And as you can see, I have used this analysis very extensively in this paper, right? दिख रहा है आपको? Create beautiful images, your paper will definitely get published, right? दिख रहा है?
यस.
Show very interesting hydrogen bonding dynamics जो मैंने ये पेपर में लिखा है. You can read this paper if you wish as to how is that you would express these results as such. Okay. तो एक बात तो समझ में आ गई आपको कि ये जो डिस्टेंस बेस्ड एनालिसिस मैं आपको बताने वाला हूँ कि हाउ इज दैट यू प्लॉट द हाइड्रोजन बॉन्डिंग डिस्टेंस, हाउ इज दैट इट इज टू बी यूज्ड. ओके, और मैंने ये पेपर में कैसे यूज किया.
यस.
Okay, so now let me tell you how is that you draw this graph. It seems really very interesting, नहीं क्या? Initially
यस
10
सर.
nanosecond तक there was no hydrogen bond, then similar and then dramatic you can say rearrangement took place in our structure during MD simulation, and again it form a hydrogen bond that somehow remain intact throughout the simulation, right?
यस.
And then I have kind of showed it in pictorial representation as such. देखो यहाँ पर दोनों के बीच में distance कितना था? 9.76, but later on 49550 पिकोसेकंड पर इट वाज 2.7, यानी कहाँ पर 49550 कहाँ पर हो सकता है? इसके आसपास, राइट? तो इस तरीके से आप क्या कर सकते हैं? यू कैन टेल कि एट दिस पर्टिकुलर टाइम स्पैन the hydrogen bond was found to be like this. At this particular time span, the hydrogen bond was found to be like this. Okay?
यस.
So try to use innovative ways to express your data. Right? Now I will tell you as to how do we create such a graph. तो काफ़ी सिंपल है, कोई दिक्कत नहीं है. What I will do is that let us load our ionize.psf, right? ये समझ में आ गया आपको? Shall I close this Discovery Studio thing?
यस सर.
ओके, अगर आपके पास में श्रोडिंजर होगा तो श्रोडिंजर में भी आप 2D इंटरेक्शन बना सकते हैं, राइट?
यस सर.
बट दिस डिस्कवरी स्टूडियो इज फ्री ऑफ चार्ज, एटलीस्ट उसका विजुअलाइजर, देन यू कैन यूज दैट थिंग. Okay, now let us load the trajectory. Let us load the recentered one. राइट, तो एक बार ये हो गया आपका. Now, what is that we want to do? We want to focus our attention on this methionine 522, right, and the hydroxyl group. So we would have to prepare a representation that will have only these two molecules, right, so that we can clearly see what is exactly happening over there, right? So first job would be to create a representation where we have only methionine 522 and our ligand molecule. I will tell you how is that we do it, right? तो उसके लिए you have to go to graphics and then representation, right? So we would create a representation that will focus first on methionine 522. So we know the residue ID, right? So we will go to this keyword section and select all residue ID that contain क्या था वो 522 and create a representation. I will delete this representation, right? So this is our methionine group, and most probably it will form hydrogen bond via its backbone, right? And then we
Yes.
need another group which we are interested in. We know its name, right? इसका नाम क्या था? इसलिए since we know its name, we can use this res name keyword, right? Residue name, and the name of our residue is ligand, right? And then we can create this representation. Now we have both of those, right? So now you can
Yes.
clearly see यहाँ पर क्या हुआ, देखो कन्फर्मेशनल चेंज हो गया एट दिस पर्टिकुलर पॉइंट. ओके, initially, you know, the distance between this atom, I mean the oxygen atom, and this oxygen atom was very high, right? Well, now let us try to figure out कि भाई ये कैसे करते रहते हैं अपन. तो वो करने के लिए I have already given a kind of instruction set for you. You can use that instruction set. Okay, after creating the representation of this protein and your ligand molecule, now what we will do, तो अभी आपको करना ये है कि on your keyboard the 2 नंबर का जो की होता है, राइट, आपके फंक्शन कीज जो होते हैं, वो फंक्शन कीज के नीचे यू हैव टू 1 2 3 4 का नंबर रहता है ना वहाँ पर, that
Yes.
2 you will have to push. Now you can see that my mouse is having this arrow, right? ये माउस क्या है मेरा, हल रहा है एरो से. नाउ व्हेन यू पुश दिस 2 number button which is exactly present below this F1 function button, right? तो उसको 2 प्रेस कर दिया मैंने, तो it became what, it became a plus. That means that it means that now you can select anything, right? Now you would select the oxygen atom that you are interested from your ligand, and you would select another oxygen atom जिसके साथ में हाइड्रोजन बॉन्ड होने वाला था, I mean this one. Now it is showing that the distance is what, distance is
Nine, nine, sub
9.76,
9.76.
right, which is quite fairly present over here, 9.76 दिख रहा है.
Yes, sir.
Okay, so this is the frame that I might have taken a screenshot of, right? इसको
सर
यहाँ से
बटन कौन से दबाने सर, एक बार दोबारा से बता
F1
देंगे सर.
के नीचे का 2.
अच्छा F1, अच्छा 2 के साथ माउस पे क्लिक करना है.
नहीं नहीं, उसको अंदर लेके जाओ और 2 बटन दबा दो. दैट दैट एरो विल कन्वर्ट इनटू प्लस,
प्लस, ओके सर.
राइट? और माउस मोड को अगर आपने फिर से ट्रांसलेट या फिर माउस मोड को फिर से रोटेट कर दिया, तो यू कैन कम आउट ऑफ दैट फंक्शन, राइट? तो अभी आई हैव अगेन चेंज इट टू एरो. ठीक है. Now let us play this trajectory slowly so that you can see what exactly happened with this hydrogen bond or this bond. Initially ये hydrogen bond इसको अभी नहीं कह सकते अपन. Why? Because hydrogen bond exists around 3.5 Armstrong या उसकी नीचे, right? तो अभी ये hydrogen bonding distance में नहीं है, बरोबर है? Now
Yes.
if I play the trajectory, major rearrangement happens now. देखो, now this particular, देखो, just I will stop. Major rearrangement happened and your hydroxyl group came closer to each other, right? You can use this mouse and then translate mode. तो इसको अपन ऐसे यहाँ पर भी ला सकते हैं. Again change the mouse to rotate mode, right? So in this way you can focus on your hydrogen bond, right? And the same hydrogen bond remain intact till the end of your simulation. So this is how
Yes.
you can visually see it. You can create a video out of it if possible, as I have demonstrated you in my previous video, right? But how is that we represent in a paper? Paper में तो आप वीडियो नहीं डाल सकते ना, तो इसलिए इसका ग्राफ बनाएंगे अपन, right?
Yes.
इसको लूप वंस कर देते, ठीक है. नाउ हाउ इज दैट वी सेव दिस डिस्टेंस? तो उसके लिए, इसके लिए आपको क्या करना पड़ेगा? यू विल हैव टू यूज दिस ग्राफिक्स मेनू रहता है यहाँ पर, ठीक है. आई एम नॉट टॉकिंग अबाउट ग्राफिक्स एंड रिप्रेजेंटेशन. ग्राफिक्स मेनू में यू हैव गॉट दिस लेबल ऑप्शन, राइट? तो लेबल ऑप्शन में व्हाट यू कैन डू, नाउ initially when as a default atom is selected, but now what, and these are the two atoms that are shown over here that we have selected, right? But instead of atom, not you, what you can do, you can change it to bonds, right? And now you can select this thing, right? और select होने के बाद में, okay, what you can do, you can activate this graph tab and use this save button, right? And you can directly save it as an all files as the name of that hydrogen bond that I have already saved it, right? You can say H bond किसके बीच में है वो? Methionine 522 and ligand का OH, right? And directly save it as XLS file, right? Save it, done. Okay, यहाँ पर आ गया ये, right? You have saved it. So I have already saved this thing, so I will show you how is that we do it. XLS फाइल में सेव किया है तो इसको डायरेक्टली ओपन कर सकते हैं आप, राइट? यू कैन गिव द नेम ओवर हियर, राइट? मैंने इसको ये भी करके रखा है, इसको प्लॉट भी करके रखा है, राइट? तो पहला इसको आप दे सकते हैं व्हाट इज द फ्रेम. यहाँ पर क्या है? दीज आर ऑल इन फ्रेम नंबर्स, बट इन पेपर आई हैव शोड इट इन रेंज ऑफ पिको सेकंड, ठीक है? तो आप ये पिको सेकंड के इसमें भी कर सकते हैं इसको, राइट? इट हैपन ड्यूरिंग, वेल से फॉर एग्जांपल 100 नहीं होगा, ये 50 पिको सेकंड का है ना, 50 पिको सेकंड का है, मतलब ये 50 रह सकता है. ओके, अप्रोप्रिएटली यू कैन सिलेक्ट द स्केल. ओके, मैं यहाँ पर करूँगा नहीं, बिकॉज आई डोंट रियली रिमेंबर द कैलकुलेशन. करना सिर्फ इतना ही है कि इन दोनों को सिलेक्ट करके गो टू इंसर्ट एंड इंसर्ट अ स्कैटर डायग्राम. आ गया. एंड ऑल यू हैव टू
Yes.
डू इज टू मेक इट फैंसी, राइट? जैसा अपन ने पहले किया था. एंड इवेंचुअली एड द फिगर्स, ये वाले ऐसा तैयार करके योर फिगर विल बी रेडी, बरोबर है?
Yes.
So this is the raw
Yes.
data, this is the raw data, and this is the final data you are supposed to present, right? You might take some time to do these things, to draw these things properly in a fancy way. बरोबर है?
Yes, sir.
So this is how you perform cluster analysis.
Got it.
Got it? And this is how you
Yes.
use it. Okay, I have already shared this paper with you. Okay, you can read it out. Okay,
Yes,
तो
sir.
देखो 6 इम्पैक्ट फैक्टर वाले भी पेपर में आपका डेटा जा सकता है,
Yes, sir.
राइट?
सर
दैट इज
तो स्पेसिफिकली क्या क्या उसमें इंक्लूड किया है सर आपने पेपर में, डॉकिंग, डायनेमिक्स और
डॉकिंग, डायनेमिक्स, उसमें तो मैंने एमएमपीबीएसी भी यूज नहीं किया था, ओनली डिस्टेंस बेस्ड एनालिसिस, राइट? आरएमएसडी आरएमएस है, और ये कुछ डीएफटी बेस्ड एनालिसिस किया था मैंने, होमोलुमो वाला, क्वांटम केमिकल प्रॉपर्टी एनालिसिस ऑफ फ्लेवोनॉइड, ठीक है? So with these simple things, if you write it properly, you can definitely score impact factor 6 or so. नहीं क्या?
यस सर.
So it is all up to you how is that you present your data. नहीं क्या?
यस सर.
Okay, so let us finish this topic now. कुछ पूछना है इसके बारे में आपको?
नो सर, ये तो क्लियर है.
Clear है? Okay. Now let us move on to the finale, free energy estimation. Okay. तो पहले ये बताता हूँ कि भाई ये फ्री एनर्जी एस्टिमेशन होता क्या है, right? And then I will demonstrate you how is that you install the software that are required for free energy estimation, because that is really very important, otherwise things will not work, right? And then I will demonstrate you how is that we use it. Okay, so let me stop stop my sharing now. Okay, so let us talk about free energy estimation. So the thing is that whatever methods that we are going to use, what we call it as MMPBSA and linear interaction energy. Okay, so these methods are included in a specific type of free energy estimation technique called as endpoint estimation method. Okay, इन्हें क्या कहते हैं अपन? We call it as endpoint free energy estimation method. Okay, so इन्हें endpoint इसलिए कहा जाता है because we sample the ensemble data, or what we can say, we sample the data required for free energy estimation from the final stages of our trajectory, where we assume that our system is in you can say is in a well converged state. Okay,
यस सर.
तो अपना जो ट्रेजेक्टरी रहेगा उसके जो लास्ट वाले फ्रेम्स रहेंगे, अपन उसमें से डेटा सैंपल करेंगे फॉर कैलकुलेटिंग द फ्री एनर्जी ऑफ आवर प्रोटीन लाइगैंड कॉम्प्लेक्स. ओके, एंड दैट इज व्हाई इट इज इंक्लूडेड इन एंड पॉइंट फ्री एनर्जी एस्टिमेशन टेक्निक. ये जो दोनों फ्री एनर्जी एस्टिमेशन टेक्निक्स है, LIE and MMPBSA, these both of these techniques are endpoint estimation techniques. That means they will extract data from the last few frames. Okay,
यस सर.
so let me tell you how is that we first configure it, and then I will tell you how is that we use it, right? Okay, now I hope my screen is visible now again. दिख रहा है?
यस सर.
My screen is visible, right?
यस सर.
Okay, so now let me tell you how is that first we configure our software. तो इसके लिए we are going to use a software called as Cafe, right? So you can search in Google like Cafe plugin VMD, right? तो यू कैन ये यहाँ पर इसका पेपर है, यू कैन डाउनलोड द कोड फ्रॉम दिस गिटहब पेज, ठीक है। बट द प्रॉब्लम इज यहाँ पर इनका if you follow this page, they have shown some examples and everything, right? But if you try to implement it or use it as per their instruction, nothing works. I don't know. We have kind of then finally figured out that what was the exact problem, right? So we had to uh, make a lot of changes in its code, we'll say, for example, right? And finally now we have modified their code, and you can use whatever that I am providing you as this is not the same code that it is present over here जो उनके पेपर में है, right? Whatever I am sharing you is the modified code जो चल रहा है, okay? बात समझ में आ
Yes,
रही है
sir.
आपको? तो the thing is that I have to make it happen. A lot of coding has to be done in order to make it workable, right? तो आप चाहो तो ये वाला भी करके देख सकते हैं. If it work on your PC, then that is well and fine. Okay, no need to use whatever I give you, right? You can use the original one. But if it don't work, then you can use whatever I am teaching you here. Okay, so let me tell you as to how is that you need to install and configure it. तो करना बहुत सिंपल चीज़ें हैं, right? So we would be using this APBS software for calculating the PB term, ठीक है? MMPBSA, इसमें से MM stand for molecular mechanics, PB stand for Poisson Boltzmann and SA stand for surface area. तो ये जो PB का टर्म है that is calculated by APBS, ठीक है? MM terms are calculated by NAMD and SA terms are also calculated by you can say SA terms are also calculated by your NAMD, ठीक है? तो आपको अगर बताना होगा मुझे, I will show you the expression of MMPBSA. कहाँ पर था? गूगल पर भी मिल जाएगा. यस, दिख रहा है ये MM molecular mechanics. ये जो free energy contribution है that is calculated using NAMD, and PB जो term होता है that is calculated using our APBS, और SA that is surface area is again calculated using NAMD. ओके, तो ये
Yes, sir.
इक्वेशन में ये जो तीन चीजें हैं those would be calculated from NAMD. This will be calculated from your APBS and this will be calculated again from NAMD. ओके, तो इसको अपने को APBS लगने वाला है. ओके, so what you need to do is that you need to copy this folder, APBS वाला जो folder है, into your C drive. Make sure that you copy and paste this folder in your C drive like this. Okay, होएगा?
Yes, sir.
Will it become possible? ठीक है.
Yes.
Then the next thing that you need to do is to copy the folder cafe 1.0 at location C program files University of Illinois का जहाँ पर भी है I will show you. Okay, go to C drive, program files x86, then University of Illinois, उसके बाद में VMD, and where is that? It says then plugins no arch TCL, plugins no arch and then TCL. Okay, in this folder you need to copy the cafe 1.0 folder. ठीक है, जो मैंने आपके डिस्ट्रीब्यूशन में दिया है. आई हैव ऑलरेडी कॉपीड इट ओवर हियर, तो यहाँ पर दिख रहा है आपको, राइट. यू हैव टू पेस्ट इट ओवर हियर. इज इट
Yes, sir.
ओके?
Hmm.
तो ये कहाँ से लेना है अपने को? दिस वन, यहाँ से कॉपी करना है और यहाँ पर पेस्ट करना है इन TCL फोल्डर, राइट.
Yes, sir.
ओके, तीसरी चीज आपको करनी है, ये जो टोपो एटम डॉट TCL है इसको रिप्लेस करना है, यानी ऑलरेडी वहां पर रहने वाला है, राइट. तो ये कहाँ पर करना है आपको? TCL में टोपो टूल्स 1.5 नाम का एक फोल्डर रहेगा. प्लगइन TCL टोपो टूल्स, ठीक है. और इसमें ऑलरेडी एक फाइल रहने वाला है, राइट. टोपो एटम्स डॉट TCL, कहाँ पर है टोपो एटम्स? ये वाला. वहाँ पर ऑलरेडी रहना है, बट वहाँ पर आपको मैं जो दे रहा हूँ वो वाला फाइल रिप्लेस करना है, राइट. तो देखो, ये बाकी के सारे 2014 के फाइल्स है यहाँ पर, और ये टोपो एटम डॉट TCL 2016 का है, राइट.
Yes, sir.
तो ये यहाँ पर डालना है, राइट. दैट मीन्स दैट दिस इज न्यूली एडेड, बरोबर है. So now make sure that you do all of these things with administrator privileges in your PC. तो जो अकाउंट से आप लॉगिन कर रहे हैं उसको एडमिनिस्ट्रेटिव प्रिविलेजेस रहने चाहिए, जब भी ये चीजें होंगी, अदरवाइज नहीं होगी, राइट.
Yes, sir.
सो जस्ट मेक श्योर कि अगर दीज आर ऑल टेक्निकलिटीज कि बाद में मुझे लोग कहते हैं कि सर ये कॉपी नहीं हो रहा है, तो आपको वो राइट्स ही नहीं रहेंगे तो आप कॉपी कैसे करेंगे? ओके.
Yes, sir.
So make sure you do everything in administrative mode rather than any simple user mode. Okay, so when you do these three things, you have configured your you can say cafe tool properly. Okay, now I will tell you how is that we use it. Okay, तो MD वर्कशॉप में फ्री एनर्जी एस्टिमेशन का लेट अस डू MMPBSA, राइट. तो ये जो MMPBSA है, इसके लिए आपको वेल यू नो व्हाट यू नीड, whatever files that you have generated during trajectory formation or during simulation, उसमें से अपने को आपका DCD फाइल लगने वाला है, राइट. द पैरामीटर फाइल ऑफ योर प्रोटीन, द पैरामीटर फाइल ऑफ योर ligand एंड अ PSF फाइल, राइट. तो जितने भी पैरामीटर फाइल्स आपने आपके सिमुलेशन में यूज किए थे वो सारे के सारे पैरामीटर फाइल्स अपने को यहाँ पर लगने वाले हैं, along with the structure file, PSF file and the DCD file, right.
Yes, sir.
ठीक है. And what I have done is that I have created a command. अगर ये कमांड को आप नोटपैड में ओपन करोगे तो ये एक बहुत बड़ी कमांड है, राइट. So I will tell you as to what this command is, so that all you have to do is to change the name of this particular ओके. तो ये कमांड क्या कहती है बेटा कि MMPBSA will activate the MMPBSA tool in your VMD dash top, यानी क्या, however or whatever topology file are present in your system उनका नाम यहाँ पर देना है. तो what is the topology file that we are using? ionize.psa. to give the name ionize.psa, right. then we उसके बाद में क्या है, dash trj, राइट. डैश TRJ, या इसके आगे आपको क्या लिखना है कि व्हाट इज द नेम ऑफ द ट्रेजेक्टरी फाइल दैट यू आर यूजिंग. द नेम ऑफ द ट्रेजेक्टरी फाइल इज prod.dcd, राइट. ये एक DCD फाइल है, therefore prod.dcd. डैश आउट में क्या बताना है आपको, what will be the name of the output file, जैसे कि ये यहाँ पर 7a.log फाइल है, you can change this thing. Okay, now this is really very important. तो डैश पार में आपको पैरामीटर फाइल्स बतानी है. सो द फर्स्ट पैरामीटर फाइल दैट आई एम यूजिंग इज दिस पैरामीटर फाइल फॉर प्रोटीन. तो डैश पार देकर पहला आपने बताया कि भाई इसमें मेरे प्रोटीन के पैरामीटर्स है, राइट. देन अगेन यू हैव पैरामीटर फाइल फॉर ligand. उसके लिए अगेन यू विल गिव दिस डैश पार कमांड एंड टेल कि आई हैव गॉट ligand पैरामीटर्स इन ligand.par फाइल. उसके बाद में यू वुड टेल कि the very first frame in your analysis should start out with frame number 900 and the last frame in your analysis MMPBSA calculation is 9999. तो मतलब अपन ने कितने फ्रेम यूज कर रहे हैं इन आवर MMPBSA कैलकुलेशन, लास्ट 100 फ्रेम्स. ओके, डू यू गेट दिस थिंग?
Yes, sir.
ओके,
Yes, sir.
तो इसके बाद में यू कैन चेंज ओवर हियर. आप चाहो वो फ्रेम रख सकते, 50 to 100 भी रख सकते, सो दैट द MMPBSA कैलकुलेशन विल बी कैरिड आउट फ्रॉम 50th फ्रेम टू 100th फ्रेम. 10 फ्रेम का भी कैलकुलेशन कर सकते आप, नो प्रॉब्लम विद दैट. ठीक है, बट यूजुअली लास्ट फ्रेम यूज होती है और 50 से 100 के बीच में ज्यादातर लोग यूज करते हैं, राइट. सो इट इज ऑल अप टू यू व्हाट इज दैट यू वांट टू यूज. मैं बताना चाहता हूँ कि कहाँ पर क्या है. देन ये डैश कॉम क्या बताता है आपको कि भाई व्हाट आर द सेगमेंट दैट कंस्टिट्यूट योर प्रोटीन लाइगैंड कॉम्प्लेक्स, राइट. तो ये इंफॉर्मेशन आपको आएंगी यहाँ से ionize.psf से, राइट. ionize.psf में नाउ यू नो दैट योर सेगमेंट A is for protein and segment name lig is for your ligand, right. तो यहाँ पर अपन क्या बता रहे हैं, we are telling कि complex is constituted by double quote में segment A and segment lig. Okay,
Yes.
that these two together form a complex. Then dash rec क्या बताता है कि which is the receptor in your protein ligand complex. तो अपने को मालूम है अपने इसमें रिसेप्टर कौन सा है, segment name A. तो I have given seg name A. Then you would also have to tell what is the ligand. डैश लिख के बताएगा कि आपके कॉम्प्लेक्स में ligand कौन सा सेगमेंट है, seg name lig. ठीक है, और उसके बाद में जो कुछ भी है you don't have to change anything unless and until you are really very sure what is that you are doing. Okay,
Yes.
ये बाकी की चीजें रहने दो. दीज आर ऑल पाथ्स फॉर APBS एंड दीज आर ऑल पाथ्स फॉर यू नो आपका NAMD कहाँ पर है, ऐसे के लिए कहाँ से होने वाला है, राइट. तो डोंट चेंज दोज थिंग्स अनलेस एंड अंटिल यू आर रियली वेरी श्योर व्हाट यू आर डूइंग. आपको चेंज कहाँ पर करना है, ये सारी चीजें जो मैंने यहाँ पर बताई.
Yes, sir.
ओके, सो नाउ लेट मी टेल यू कि भाई ये हो गया आपका कमांड जो रन होगा आपके VMD में. नाउ हाउ इज दैट वी रन दिस थिंग. ओके, ये भी बता देता हूँ आपको सो दैट थिंग्स विल बिकम क्वाइट रियली वेरी क्लियर टू यू. ओके, नाउ ऑल वी हैव टू डू इज टू स्टार्ट VMD. राइट, go to extension analysis TK console में भी, राइट. TK console में जाना है. We need to change our working directory to जहाँ पर अपने सारे input files है. So now since we have started in VMD, that means we are in C drive. We would have to change it to, sorry, we are in VMD, right? CD G drive, right? And then directly go to the working directory. And hit enter. Okay, so now you are in working directory. Just hit लिस्ट आउट ऑल द फाइल्स दैट आर प्रेजेंट, ls कमांड से वो हो जाएगा, राइट. देन this is it. Okay, so now how do we use that MMPBSA? Okay, so now we would have to first tell our software that uh, we need to import cafe, right? तो उसके लिए अपने को क्या करना पड़ेगा, we would have to give command like package require cafe 1.0, hit enter. now ये यहाँ पर 1.0 आ गया, मतलब क्या है, कैफे हैज नाउ बीन यू नो activated in VMD, you can say. Okay, so after doing this, you can simply source this command file. Okay, like we have been sourcing that pgn file and all the text files or all the scripts that we have been using, बस वैसे ही करना है. source command dot txt and hit enter. बस that's it. Now it will do all the calculation. Now you can see that it is now calculating molecular mechanics term. So it might be using NAMD. Then it will calculate the PB term. For it, it will be using APBS. Then it will be calculating SA term, right? And for that SA term, it will again shift on to NAMD. All these things happen in background. Well, I know these things because I have coded that. I have modified the lot of codes.
Yes.
Okay, you would have to remain patient, right, till it kind of finish off with this thing. Okay, तो अभी आधा पौन घंटा रुकने का, या shall I close this thing?
Sir, we can close.
हाँ, we
Sir,
can
we
close,
can
है,
close.
क्योंकि
Yes.
रिजल्ट अपने पास में है. And once everything gets over, everything finishes off properly, then you will get this log file, ठीक है, and you can edit it in any text editor. Okay, now it will tell you कि okay, for complex the electrostatic interaction contribution was this much, van der Waal contribution was this much, PB contribution was this much, right, SA contribution was this much, gas constant was this much, solvation constant was this much, polar non-polar contribution, everything. You would be interested in this delta column, right, and this is the final binding free energy, right? So
Yes, sir.
whatever free energy values that are reported in literature, दिखे थे ना अपने को, ये जो दिख रही है आपको, solvation energy, electrostatic energy, van der Waal energy, Sasa energy, well, these are these value, electrostatic energy, van der Waal energy, and you should report values from this column. Why? Because this is delta value. Okay, over here you have got the final total free energy change, and this is its standard deviation, plus or minus 1, right? So I hope now you get as to how do we work with this thing. समझ में आया?
Yes, sir.
So use these
Yes,
things
sir.
really really very carefully, right? इसे बंद कर देता हूँ मैं अभी. It will take some time, it will happen. अभी भले ये not responding बोल रहा है, but it will respond after the calculations are over. Maybe I have left some bugs in my code, but trust me that it is working. Right, so you
Yes.
don't have to worry.
सर एक क्वेश्चन पूछना था.
हाँ.
सर जैसे मैंने भी सर यूजुअली जैसे आपने बताया कि अपन ने लास्ट के फ्रेम्स उसमें से ले लिए 900 से 999 तक. अपन ने जो फ्रेम्स मतलब जो अपन ने यूज करे हैं एमएमपीबीएस से कैलकुलेट करने के लिए. बट जब सर हम लोग एम फार्म में थे और श्रोडिंगर पे काम करते थे तब हम लोग डायरेक्ट डॉकिंग के बाद ही एमएमजीबीएस से कर लेते थे.
हाँ, MMGBSA श्रोडिंगर में होता है.
हाँ, तो सर पर वो हम डायनेमिक से पहले ही
कर लेते थे, होता है, इट इज पॉसिबल. वेल, MMGBSA इज कंप्लीटली डिफरेंट आइडियोलॉजी,
ओके।
राइट.
हाँ, और सर मैंने सर एक वो भी पढ़ा था, मतलब मैंने लिनक्स में एक रश्मि कुमारी करके एक वो है,
हाँ,
उनकी
वो
भी फाइल
ग्रोमैक्स,
मैंने।
ग्रोमैक्स में यूज होता है.
हाँ हाँ सर, ग्रोमैक्स
बरोबर.
में। उसमें भी सर शायद अपन लोग उसमें भी शायद एमडी के बाद ही कर सकते हैं,
हाँ,
जहाँ
उसमें
तक
भी एमडी के बाद में ही होता है.
एमडी के बाद
Right.
होता
So if you use GrowMax, then you can use Rashmi Kumari script.
है।
Or if you use NAMD, then you can use this cafe plugin or whatever I have done.
यस।
Right. तो ये हो गया MMPBSA. Then we have got another method called as linear interaction energy. Right. तो linear interaction energy का भी आपको थोड़ा सा मैं background देता हूँ. Okay, here it is. So linear interaction energy is, quite easy. Okay, so what we need to do is that over here we need to perform two simulation, right? First, we need to perform simulation of our ligand in complex with protein, right? जैसे कि यहाँ पर बताया ligand that is bound to protein, and we have to perform a separate simulation of only ligand, what we call it as free ligand.
यस।
Okay, and when you do this thing, you would extract the values for your free energy calculation from last 100 or 500 or 50 frames, and you would try to measure what is the energy difference in terms of van der Waal energy when it is present in bound state and when it is present in free state, and what is the free energy change in this electrostatic contribution when your ligand is in bound state and when your ligand is in फ्री स्टेट. बिसाइड्स दिस, तो ये जो वेंडर वॉल और इलेक्ट्रोस्टैटिक एनर्जी है विच यू आर supposed to calculate for ligand in bound state and in unbound state, ठीक है, these are to be calculated from trajectory. Okay, and इसके अलावा you would need three empirical parameters, alpha, beta and gamma, right? So people usually use this default value. Okay, so you can use the same default value that are already coded in the program, but ideally you are supposed to use some statistical model to fit these values properly. Okay, I will share that paper wherein people have told as to how you do it properly. Okay, but most of the papers, they use the default values and it also get accepted, so no big deal with it. But technically speaking, you should properly calibrate this alpha, beta and gamma parameters, or what we call it as empirical parameters, and feed them appropriately in your uh, you know linear interaction energy model that is said. Okay, so uh, we will not go in details of how is that we calibrate it considering the time that we have today. Okay, but there are a lot of paper that are published, as you can see, with default values. Okay, people usually don't know the details of all these expression. All they know कि यहाँ पर आपका delta G मिल गया मतलब बात खत्म. Okay, but if you ended up with a very seasoned molecular modeling reviewer, then he will ask as to what is that you have done with this alpha, beta and gamma parameter, and then you would have to eventually do it. Okay, I usually you know try to first try to publish it with the default value who want to do the extra work. right? And if it really don't work, and trust me, I haven't I haven't encountered any reviewer who ask me ki okay, how is that you have calculated the alpha, beta and gamma parameters. So it will work. Okay. Don't worry about it. बट आपको पता रहना चाहिए, इसलिए मैं बता रहा हूँ. ठीक है.
यस
ओके. तो इन दिस LIE, this is the you can say production of your only ligand. I call it as prod free. Let me show you. Right? इसमें आपको दिख रहा है क्या? You see only the ligand molecule in water box.
यस सर
Right? So you have to perform this simulation separately if you want to use LIE model. Right?
यस सर
And this is the simulation that has the same ligand bound with your protein. So in this way, we have protein ligand system in water molecule. We would need that. And as I have already shown you, we need another separate simulation of only water molecule in ligand. Right? And your LI model will calculate the electrostatic and van der Waal differences when your ligand goes from free state to bound state. And along with this empirical parameter, you have a linear interaction energy model that will give you the free energy estimation. That is how it conceptually works. Okay. Okay. So for this simulation, let me tell you as to ये बहुत जल्दी हो जाता है, क्योंकि इसमें अपने को पीबी टर्म यूज कैलकुलेट नहीं करना पड़ता है, एंड यूजुअली पीबी टर्म टेक्स अ लॉट ऑफ टाइम, एंड वी डोंट हैव टू कैलकुलेट द एमएम टर्म्स एज वेल. राइट? सो ऑल वी हैव टू कैलकुलेट इज इलेक्ट्रोस्टैटिक कंट्रीब्यूशन एंड वैन डर वाल इंटरेक्शन, जो आसानी से और बहुत जल्दी हो जाता है. Okay. So now, if you are using these commands that I am giving you, make sure that you give the names the way I have shown over here, or whatever the name of your files are, you need to change those names in your command as well. Okay. So make sure that everything is in harmony. Okay. So over here, as you can see, like LI will activate the linear interaction energy model in your VMD. Dash top bound, this will tell ki bhai what is the bound ionized bound topology of protein in complex with ligand. Then you would have to tell what is the trajectory of bound. That means the trajectory जिसका नाम क्या है, wherein the name of the trajectory in protein ligand complex. Then similarly you have to give the topology of free ligand, right? And then the trajectory of free ligand. Okay. उसके बाद में क्या दिख रहा है आपको? What would be the name of the output file, right? Then what are the parameter files that you have used? This particular first parameter will list out ki bhai what is the parameter of my protein molecule. The second parameter command will give the idea as to what is the parameter of my ligand molecule, right? Then what is the first bound का जो फर्स्ट फ्रेम कौन सा रहने वाला है 900 टू लास्ट बाउंड फ्रेम वुड बी 999. ठीक है. नाउ यू आर गिविंग द सेम फॉर लाइगैंड. लाइगैंड का डेफिनेशन क्या है आपकी पीएसएफ फाइल में, राइट? उसका फर्स्ट फ्री का कौन सा स्टेट है और फ्री का लास्ट वाला कौन सा स्टेट है, फिर लाइगैंड का डेफिनेशन क्या है, राइट? इट इज नेम एज seg namely and don't change anything later on, right? बात समझ में आ रही?
यस
Done. So all we have to do, this is what this command will work if you are trying to use the default value for gamma, for alpha and for beta, right? Now if you want to change the value, तो आपको कमांड में उसके रिस्पेक्टिव ये चेंज करने पड़ेंगे, पैरामीटर्स डालने पड़ेंगे, राइट? ये करना पड़ेगा आपको. डू यू गेट दिस थिंग? क्या बताया मैं? आई हैव स्टॉप टिल गिविंग द कैसे कहाँ से लाना है, बस उतना ही मैंने बताकर रोक दिया है. वाई? बिकॉज आई डोंट वांट टू चेंज द अल्फा बीटा एंड गामा पैरामीटर. आई वांट टू यूज द डिफॉल्ट. अगर आपको वो चेंज करना है तो यहाँ पर वो डालने पड़ेंगे.
यस
Okay, so now the thing is quite really very simple. Okay, all we have to do, जैसे वो किया था वैसे भी ये वैसे ही इसे भी रन करना है. VMD ओपन करो, change the working directory to the place where all of your files are located. Just hit enter. So now you are in LIE. Just list out if all the files are present, right? Now we would have to activate the LIE in our VMD. So for that we need to first import package cafe. So उसके लिए command क्या था? Do you remember? Package require cafe 1.0. तो देखो मैंने यहाँ पर क्या दिया, कैपिटल दिया एंड इट कैन नॉट फाइंड इट, राइट? तो आपको वो स्मॉल में ही देना है. Now it can locate it. Why? Because when I pasted that thing, the folder name is with small c. Okay, ठीक है, यहाँ तक हो गया. Then
Yes, sir.
once we have imported cafe, all we have to do is to source command dot txt. ठीक है, ये log file को I will rename it to log x so that new log file can be created. This won't take much of the time. इससे ज़्यादा टाइम नहीं लगता है. ओके, द लास्ट टाइम व्हेन आई डिड दिस थिंग, उसका लॉग फाइल अपने पास में है. इफ आई ओपन इट विद नोटपैड, ओके, इसका इस तरीके से आपको रिजल्ट आएगा इसका, राइट? लाइक यू यूज्ड 100 लास्ट फ्रेम So in the bound state, the van der Waal contribution was minus 42 and the electrostatic energy was minus 36. In free state, the same was like this, and the delta value after putting all of these value, keeping alpha 0.18, beta 0.33 with gamma 0, which appropriately is the same thing, near about the same thing, as you can see. 0.16, यहाँ पर 0.18 है, right? Then beta is 3.5, ठीक है, gamma 0 था, यहाँ पर भी 0 है, beta is 3.5 something, right? 0.33. ये default value है. If you want to change, then you would have to add the required value in your command. Beta is 0.5. Over here we have used the beta value for 0.33, right? Yes, it took only 39 seconds, right? And you can see the same log file. Minus 19.6033, और जो लास्ट टाइम कैलकुलेट किया था वो वही एग्जैक्ट वैल्यू आया, minus 19.6033. That means the computation are very consistent, right?
Yes.
Okay, so with this we can conclude our workshop, right? And one more thing that we cannot do is that but uh, I have kind of we have discussed ki if time permits we can do that MD on web or cloud computing platform, बरोबर है?
Uh, yes, sir.
तो वो मैंने क्या किया है, I have made a YouTube video, right? And I have recently shared that YouTube video. You can try do it accordingly there. Just a minute. I think the net speed has slowed down. Right? This video 2 days ago I have uploaded. Performing MD simulation on cloud platform using Google Colab. It is another 35-minute video. Okay. Shall I continue showing it?
No, sir, we can see that, and if we
How
might
to
be
run
having any
an
doubt,
MD
then
on video. It is
we will
quite
ask.
really very user friendly. You can just check it out. Okay. If you need files and everything, I will give you.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Right. It will again take some 35 minutes.
Yes. Uh,
So, but I kept my promise.
sir, that video, sir, I was seeing last night. So
Right.
it was quite easy to understand. So we can go through that whole video and try from our side that how to run it in the collab.
Okay. So let me stop recording.